Just like in the case of surface charge distribution, similar is the case with volume charge distribution. The only difference out here is there the charge were being distributed over one surface, was like a 2D scenario, whereas in this particular case the charges are being distributed in a 3D, in a volume. Okay, the charges are being distributed over one volume and it is distributed equally. Okay, it's like at every point on that volume the charges are going to be the same. Okay, it's like continuous system. So what we do, just like the previous case, we take a small element from this entire volume, we take a small element of the volume dV which contains a small element of charge dq. Okay, and we try to find out the force at this point acting to this q naught. When the charge is distributed over a volume of the conductor, it is called as volume charge distribution, also known as volume charge density. The symbol is rho. This is a rho. Okay, the name of this symbol is rho, which is being defined as rho will be equal to charge per unit volume. In case of line integral, we had charge per unit length, and surface integral, charge per unit surface. Now in this case it is charge per unit volume. Okay, and the unit of volume charge distribution is coulomb per meter cube because it is a volume now. So what you want to do is you have to find a force, okay, the small element of the force acting on that q naught because of that small element dV, which is going to be equal to 1 by 4 by epsilon naught q naught rho dV divided by r square with a unit vector r cap. Okay, as I said before, this dq is acting like q2, this q naught is acting like q1. Okay, and we just substitute for q1 and q2 as q naught and dq. Okay, where dq is rho dV out here. In order to find the total force, you just integrate over the total volume. So this is your volume charge distribution. If you guys are going to shout like this all the time, I'm going to take a test.